So to tackle the first problem, we're going to look at first drawing 2-iodopentane with the S stereochemistry. So we have an I here. It'll be 1, 2, 3. So if I draw it wedged, then it would be R. So if I draw it in the dashed form, this would make it S. So S2-iodopentane, we're going to do a reaction with sodium iodide in DMSO. And it says that we get a racemization in the solution. So racemization means we get mixture of stereochemistry. So some is going to be reverse stereochemistry, and some will be where it maintains the stereochemistry. So if we look at our substrate, we have a secondary alkyl halide, which can go SN2. Sodium iodide is a nucleophile that is minus, which indicates SN2 as well. And DMSO is a polar aprotic solvent, which also indicates SN2. So if we do our nucleophilic attack here from the backside, the product that we get is the same, except now our iodide is wedged. So this reaction can keep on occurring where the iodine can attack this R, or it can keep attacking the S, and that's why we get the mixture. The nucleophile is the same. The nucleophile results in the same iodide getting added, and again, that's why we get the mixture. Okay, so with number 21, we're looking at the following SN2 reaction. It first says to assign the stereochemistry of the substrate. This is 1, 2, 3. And the hydrogen is in the correct direction, so this is R. So this is R. Assign the configuration of the Chiral center in the product. 1. So this one here, our number 1, we have Cn versus C to O, and O is bigger than N on the periodic table. So this is now our 1, this is 2, this is 3. So it's going counterclockwise, which would indicate S, but our hydrogen is in the wrong direction. So that becomes R. So does this SN2 process proceed with inversion of configuration? We went from R to R, so it would seem as if the stereochemistry did not convert or invert. However, our nucleophile is the one that added a new carbon bond, and that's what affected the stereochemistry change. So yes, conversion. So Cn had a lower priority than Br, which is why the stereochemistry maintained as R. Alright, for number 23, we're going to look at how we can make each of these alkyl halides with a nucleophile. So we're going to look at what alkyl iodide is needed and the nucleophile that we would use. In order to make this compound, if we're working backwards here, we know that we can do a Cn using NaCN as our nucleophile. And we just need to have the alkyl iodide in that position. These can stay the same, nothing's happening here. And we want our iodide to have reverse stereochemistry because we're doing an SN2 reaction. So that's how you could do that reaction. So this is our leaving group, nucleophile, electrophile. For this reaction, we're looking to add an SH, so we can use NaSH as our nucleophile. And we would need the iodine again in the opposite direction of what the product is. Here's our leaving group, electrophile, nucleophile. Okay, here we're going to try to figure out what reagents we would need to make the following transformation. In reaction A, we're going from OTS to an OH, and this is an SN2 reaction where this OH is the nucleophile. So we just have to figure out what nucleophile we have. This is our leaving group. That would be the electrophile. We want to do NaOH, and that one would work just fine. For B, we have a primary. The primary on the A also tells us that we need to use an SN2 reaction, and in B also we need to use an SN2 reaction because of the primary group. However, OH is a bad leaving group, so we have to make it a better leaving group, and to do that we need tosyl chloride with pyridine, which will make the OTS, and then we can add the NaCN to get this group added. Alright, for 24, there's two potential ways for making the same ether, but only one of them is successful. Identify the one that works well and explain. Okay, in this one here, our iodine is acting as the leaving group. O- is the nucleophile, and this would be the electrophile. And this nucleophile tells me that I'm going to try to do an SN2 reaction. This wants to go SN2. But there's a tertiary alkyl halide. And we can't do SN2 at tertiary centers. In the next reaction here, we have a primary. This is a methyl actually, which is even better. And this is our nucleophile, so that could come and attack here, kick off the iodine, and we get the desired product. So this one works here, less steric hindrance. All right, here we're looking to see what reagents again we can use. This is a tertiary alcohol, and we want to put a Br here. OH is a bad leaving group. If we can protonate it first using HBr, we would get that. The water would leave. And the Br minus can come in there. So this would just grab that H and do a proton transfer. We have loss of leaving group. And the nucleophilic hug. Alright, predict which of these substrates will undergo solvolysis reaction more quickly. Solvolysis is the same thing as an SN1 reaction. So if I do an SN1 here, this is a tertiary carbocation that would form. This one would be allylic. That one is more stable. This has resonance stabilization. Alright, so here we're looking to see if this reaction is going to go SN1 or SN2 and then give the major product. Here I'm looking at something tertiary. Tertiaries can only go SN1. So we're first going to get the formation of the carbocation, and then the nucleophile can attack that. There's no rearrangements there because that's tertiary. So our product is the OMe. So we make the ether there. This one is a secondary. We have a strong nucleophile that's negatively charged and an abbreviated aprotic solvent. So this is SN2. So the nucleophile will attack there, kick that off to form Cl. Alright, here we have a tertiary again. So this is going to be SN1. Our alcohol is going to pick up a proton. And then our leaving group is going to leave because water is a good leaving group. We lose the stereochemistry there, so this gets plus. And then Br minus can now attack there. And we'll get a mixture. So you can draw it flat or you can draw the squiggles there. For this one, this is primary. NaCN tells us this is a nucleophilic or a nucleophile that's negatively charged. This is my acronym solvent, so this is SN2. That's just going to attack there. And we get CN. All right, and this one is secondary. We have NaCN DMSO, so this is SN2. And that will be CN.